Okay, start recording and okay, so okay, right time and so forth, right day of the week. Um, okay, so check something here. Uh, Okay, um, okay, so at the end of uh our lesson last Wednesday, um, we were looking at the states, okay, that a processor in, and the transition, okay, the operating system in the process control block, um, uh, that's created for every process, stores the state that that process is in, that sort of necessary information. When, okay, a process is being created, uh, and typically uh, the at least right, there might be additional, okay, items that need to be created for a process, but we had seen the two main things, in the past couple of lessons. Actually, we talked about that, at least in the past two. I don't think we haven't done too many, already dealing with processes. The process control block is the place where you store all information values and so forth for the process. That would typically be created first. Uh, it would then be the other object that a process would have would be its memory space, and what is in there. It's the main thing is its program code in the text section. The data section is really, well, it would be set up, and some of the global variables that are in there might need to can be initialized with particular values. The heap is okay. Sort of really would sort of be empty, and the stack would be empty or sort of set up. But that's all part of the memory space, and the area that process occupies in virtual memory, uh, uh, and other okay values dealing with where the process resides in physical memory uh, are pieces of information that would be kept in the process control block. We had the section we labeled okay memory management. So really the control block would have to be first, then you can set up its memory space. But okay, all during that time, okay, the state of the process, its value in that place in process control block would be okay. Its value would be new. However, we implement the values of a state. Okay, there's only a small set of states, and in doing this lesson yesterday with the other class section, the there is one state that is meant, talked about in the textbook, that currently used that uh, isn't specified in the previous textbook that I used. And I looked it up, and um, I and one of the students in that section had brought up where it was. look at it. I can, in a way, speak about it, and I know, okay, it was not one of the states that I was talking about with the other class. So it's just sort of an additional one. So uh, 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 while things are being set up for the process, the state, valley. So there's only like a really small set of states and another small set of values. So, however, you might represent typically using numbers. Each, the name that we're using, okay, would really be sort of like doing an enumerated type in programming when you want to do, a good example in programming is sometimes in your program you want to represent the days of the week, okay, Sunday through Saturday or whichever way that you, okay, sort of some calendars do Monday to Sunday, but often, okay, an enumerated type. All languages, even Java, has that. So that you use the word, okay, but in your program, an enumerated type is sort of a built-in way of before languages had that, where you create, okay, a data type and being an enumerated listing words, what you did was you created a set of constants, like making Sunday 0, Monday 1, and, well, however you may do it, and so forth. Okay, so the value in the block for the process, that would be set up first, and the state value, the the state entry in the block, okay, would be set to new. That tells the operating system that that's the new process. Once everything is set up and it's set to execute or begin executing at whatever point that is, okay, your textbook might use a different word, but it's really all okay, really means the same thing. I had kind of looked at it and they said available. So our diagram here is kind of like a graph, okay, where okay the state or nodes, okay, of the graph are the state that a process is in, okay, and the arcs really show okay when the process goes from one state to another. That would just mean that in the control block, its value would then change to okay the state that we're that the arrow is pointing to. Okay, so once it's admitted, and I think in your textbook the word admitted, okay, was instead they used the word available. The process is then in the ready state. Okay, it is not executing instructions. The CPU might not be free, or another process might have the CPU, and so this process has to. Okay, now we use the word ready, okay, to kind of distinguish from another okay type of waiting. Here is waiting to get the CPU. When the CPU is free and okay, it's the process chosen, okay, then it'll okay be able to okay execute. But until then, okay, if okay it's all set and it's just okay in a way waiting okay to okay begin executing. That's the ready state. It's waiting, but we call it ready instead of waiting. It's ready, okay, but it's not okay what we would call running, I think. Okay, so uh, there okay there can be any number of processes that would be in the ready state. Okay, and depending on how many processors you have, and those processors, if they, have multiple cores, okay, with running, okay, the number of processes that can be in that state, okay, depends on, again, how many processors you have, okay, that's hardware, and then for the processors, okay, or processors that you have, if they have multiple cores, okay, two or more cores, okay, each processor that you would have, uh, okay, um, you that, and then hey, depending on how many cores. So if a processor has a core, then you count the number of cores instead of counting the processor. If the processor only has one core, okay, then you only count that, as one. So your total count would be really specify how many processes can be okay in the running state. Okay, the number of processes that are in the ready state, okay, is independent of okay processors and cores. Okay, you can have sort of any number of them. Can't have more than the number of processes that are currently in the in the system, or in other words in memory. Um, okay, so when a CPU or core, what I'm going to do in our discussions, I'm going to limit, okay, the computer system to having, just to make it simple, one processor, and that processor only has one core. So with that system, okay, only one process would be in the running state. Okay, so when the CPU, when I say CPU, I'm talking unit processor, unit core. So when the CPU becomes free, okay, there is okay routine or task, or in other words code, part of the operating system called the and it's actually really you would call it the CPU scheduler. Okay, and there are different algorithms. We're going to look at them okay, on in in a number of classes, and each has a particular you know uh, uh, you know would be used in a particular situation. An operating system typically is coded to use a particular algorithm. Usually it doesn't. Okay, that won't change unless for some reason they redesign the operating system. But usually an operating system, depending on what the operating system is used for, okay, whatever the scheduling algorithm is, that's written, and doesn't the algorithm wouldn't change. Okay, it would always be that. So when the CPU becomes free, okay, the CPU scheduler, okay, has available, okay, to it, okay, a means of having in a way, I'm just going to use the word list of all the processes that are whose state is ready, because those are the ones that can end up in the running state. Okay, and in like I said, I'm sticking to where only one can be in the running state. Uh, okay, so you know, if there's only one process in the ready state, okay, that's easy enough to know which one will be. They call it dispatch. okay, or dispatch, scheduler dispatch, or dispatch. Okay, that process, the CPU set up so that it will then, okay, begin executing. The last thing that the scheduler does, okay, but if there's more than one, okay, process in the ready state, okay, and that depends the algorithm in a way, okay, would either, it the list of processes is organized in a particular way such that the CPU scheduler can quickly, okay, it doesn't necessarily have to choose, like I said, the list of processes in the ready state would be set up so that it can quickly get the one that uh, that um, is next in line, okay, to use the CPU, and then it dispatches it. So that process would then end up in the running state. Running state would mean that, okay, the CPU, the last thing that the scheduler really does is load the, okay, remember, I see your question, I'll get to that, just finish this tiny point. Remember, the process control block has there's an entry in, okay, that processes, okay, block halt program counter. So the contents of that would then be copied to the program counter register of the CPU, okay, and then, okay, from there, okay, the next instruction CPU executes is an instruction of the process. Okay, so Chris asks, is it proper to say the CPU scheduler dispatches processes that are in the ready state? Yeah. Okay. Now, okay. You said processes. I mean, depending on how many CPUs are, okay, and cores that you have, okay, it it would dispatch one process for each one that's free. No, the scheduler would probably handle one at a time. So it would dispatch, a process to, a core or a processor. But yeah, the only state that, okay, that they can be dispatched from is ready. Okay, that's the only state where, okay, a process can, resume um, execution. Okay, now, okay, sort of a question for everyone. A process is currently running. Okay, what could, okay, cause, I want to use the, okay, um, a process is running on the CPU, and okay, in the middle of its executing, okay, something happens where, okay, it can't continue running. It, you know, it still can, okay, but happens sort of in the middle of its execution. Okay, what could that be? What in a computer system occurs, and something that might occur frequently, okay, that might happen. Processes running and can keep running. Okay, okay, it needs an unavailable resource. Now that would be where the process, definitely can't continue running. But I said something in the middle of its execution, which would mean it had been executing and it can still execute. But Raj Kamal, okay, well, okay, you kind of covered your bases by providing both, so that, okay, in part of it you have the correct answer. Okay, okay, hardware interrupts. Okay, I mean, in the textbook I used before, this is kind of the diagram they had, but even the one that uh, that uh, uh, that you have is, similar. Though, like I said, they have an added state that I'm not including in here. Okay, in that textbook, they just labeled this as interrupt, because I think they didn't necessarily, okay, they consider an interrupt, I think, in that book as hardware interrupt. Okay, but I always like to, but I think in that book they label, okay, a system call, okay, as a software interrupt. Okay, so uh, okay. So here we're talking about the situation where it's in the middle of, okay, executing instructions. It can still continue executing instructions. It doesn't have a reason, okay, for not, okay. A hardware interrupt occurs. Okay, definitely the system has to, and we're talking about a user process, not a, well, whether that's a system, okay, program or an application program. Okay, the kernel's a bit different. Okay, often there, the kernel's not a process. It's the operating system. It doesn't run as such, and nor, well, depending on the operating system, it it might disable interrupts. What it does, okay, maybe it handles hardware interrupts. It, wouldn't necessarily want to be interrupted in the middle of something important. Okay, but in a hardware interrupt, if the running process, can still execute instructions, it's still more, okay, obviously whatever instruction the CPU is working on will finish that, but okay, if the next instruction, the process, there's another one it can execute, it can continue. Okay, the system definitely has to have that hardware interrupt handled, and if, like I said, we're dealing with uni-core, okay, processor system, in order for the kernel, okay, interrupt handler and the interrupt service routine being part of the kernel to run, okay, it routine is code, it has to run on the CPU. Okay, you can't have a process running and have the kernel running at the same time. I mean, if you have a multi-processor or multi-core system, okay, then okay, but if you don't have anything free, okay, but we're keeping it simple. At least here with unit processor to unit core, okay, you need to free up the CPU so the hardware interrupt can be handled. Okay, so the process doesn't go into a different state. It really is ready because the next thing it can do is continue executing, having its instructions execute. So it definitely goes to the ready state. Okay, and typically, okay, most CPU scheduling algorithms, okay, would be designed where, okay, if it was a hardware interrupt that, interrupted, okay, a running process, that process changes to the ready state, its state value changes to ready, but it will then go back or be dispatched, okay, right away. Once the interrupt is handled, okay, the CPU is free, okay, typically another process will not get the CPU, okay, even if there are others that are in the ready state. The one that was interrupted by by the hardware interrupt will be the one that resumes. So, okay, that doesn't necessarily have to be the case. It depends on the CPU scheduler. Okay, so in a way, you know what it does. The CPU scheduler is a task of the operating system that manages that resource. The CPU is a resource that every process needs. Okay, now, so that's one way it goes out of the running state. Okay, what other way, okay, can a running process, okay, okay, leave the running state, okay, and wait, end up in another state, okay, one that we don't have here, and what state might that be? So, that's a question. Definitely, it's a hardware interrupt that occurs, and assuming it's in the middle of having its instructions executed, it can resume. Okay, it goes in the ready state, but okay, if it's in the running state, okay, okay, our state diagram, we're having it. It goes from the running state, and what might cause it maybe to go out of the running state, and okay, what like it okay, what other state might it go into? Okay, David says block state. Okay, yeah, that's your textbook used the term block. Okay, so I'll kind of put it down here. Okay, the other name that that others might use is the waiting state. Okay, no, and I took a look at it, and it's suspended is not the same thing as blocked or waiting. Yeah, suspended, but it depends on whether or not an operating system has this particular routine. Okay, not all would. Okay, but you have that in your there. I was looking at the waiting might be a more okay. I, um, I would say it is because the textbook I used to use uh, was the textbook I used, or I didn't use it. Okay, well, I used it in when taking the course, but my instructor, same one author, okay, that is still okay an author of the textbook. The other one, for whatever reason, hopefully he's still alive and enjoying probably retirement, but it was basically, and we used, that's what I remembered. We called it waiting, but it doesn't really matter. Okay, what would cause a process to go from the running state to the block or well we like I said we can also call it the waiting state. What kind of sort of uh, thing might it would be something that the process did okay okay well David says an IO device okay like a printer but yeah any input IO device so what you mean is that okay it issued a system call, okay, and it doesn't necessarily have to do with it doesn't necessarily a system call doesn't necessarily have to deal with an I/O operation. There are other system calls that don't deal with I/O, okay, but deal with things like events. Okay, sometimes one process needs something provided, that another process, okay, provides, okay, and so, it executes a system call that puts it in the blocked or waiting state. Okay, and that would be an event and not necessarily an IO operation. But often most system calls. So Raj Kamal had said software interrupt. Okay, aka well that's system calls really aka okay software interrupt. But either one, any really system call, a process definitely has to wait definitely for an event. Okay, even if the event already occurred. Okay, it still needs to issue that, then the operating system, in a way, will when an event occurs and when an I/O operation completes okay, then definitely the process would no longer be in the blocked or waiting state. Okay, yeah, user input that it would be an output operation. That's an IO operation. So definitely, I'm going to have an arrow coming out of the blocked or waiting state, or I couldn't put it wherever what state does the process go to, okay, once it's no longer waiting, okay, the ready state, yeah, because, okay, it had to wait until, okay, that, IO operation, okay, IO, uh, or event completion. Okay, and I/O devices. I mean, you were right, David, in saying an I/O device. Okay, in order, it's a resource. Someone, I forgot if it was you or no, Chris had mentioned. Well, unavailable resource. Maybe and if it meets it, definitely it would go into the blocked or waiting state. So that's why it's not necessarily the resource might not be an I/O device. I think I looked in the textbook and they kind of talked about resource, but they were talking about it in general, terms. Could be okay, an I/O device that's a resource, and there are other resources. Okay, if it's not I/O, okay, then okay, whatever that resource event, okay, instead of using that term, we could say resource. Typically, okay, the event is okay with the resource that resource becomes available. Okay, and usually once that's there, then it goes into the ready state. Okay, now the running state. Okay, blocks. The only thing, the only reason it's there is that it needs to wait for, okay, that resource event, IO operation, whatever we want to call it, to complete. Once it's done, it's in the ready state. So that state doesn't have any other, okay, would have any other there. The running state, aren't there, is, is there going to be any other arc coming out of that state? And if so, oh, David said, the terminated state. Okay, so I see, okay, well, you definitely, okay, should have been reading, okay, on the reading, that was, I hate to say, a couple weeks ago, worth of, reading, the terminated state. Okay, now, that they're usually in code, the programmer, okay, software developer, software programmer doesn't usually, okay, put explicitly, okay, a system call, an API, you know, uh, the text of the API, but we normally call that, give it the name, okay, exit. Okay. I mean, that might be sort of the typical name. Like I said, it's not necessarily, okay, written explicitly. Okay. If you think of like a C, and, okay, I mean, okay, I know C++, I guess I'm talking about it because I gave an assignment in another class, and some people kind of, I mean, it is different, but okay, um, I stated write it in C, okay, and they were asking could I write it in C++, okay, but okay, knowing the assignment, you wouldn't use the object-oriented programming features of that is in C++. C++ was okay, you know, took C, added object-oriented programming features, classes, and you get C++. And okay, input output is a bit different, but in there, in the no, in you know, in okay, a simple kind of program, like in C, you have the function called main. Returns an int, and you typically have a return statement. Okay, that's not like, I mean, that really generates the or is where the exit system call would be. Okay, so the process definitely has to be in the running state, and the last set of machine language instructions that it executes is the code making up okay, the system call, okay, exit, that, it is the normal termination of a process. Now, a process cannot, okay, just, okay, disappear from the system. You have its process control block, okay, and its memory space. Okay, that stuff has to be freed up. So, okay, it's the memory space probably would get freed up, okay, but the block would definitely remain until, okay, all the necessary things are done. Okay, definitely its parent needs to know, okay, that child terminated. Because if it needs to terminate, then, well, I mean, it might, terminate its children, but it needs to know, okay, if, okay, that particular child process, that process, which is one of its, children, has terminated, then, that would definitely be removed from, okay, its, list of children, since it no longer exists. So, that's why you can't just, it just, get rid of the process control block, and its memory space, and not bother with a terminated state. It needs to be in there as the control block at a minimum needs to be there until, okay, whenever needs to be done. For example, alerting its parent that, okay, it terminated. That way, its parent, when it terminates it, it needs only to terminate, okay, its children, and so forth. Okay, in a way, you're getting that, experience, okay, with your project, which I hope you guys are, okay, working. I shouldn't use the term. Those of you, you as students, shouldn't use a particular pronoun or a particular, okay, gender, but all of you hopefully are working on it on your own. Okay, and I did send out an email. Okay, and so check your Queen Charlotte student email. If, okay, you don't know anything about it, then you ignore it. But, okay, you can kind of take a look at it. Okay, so those are the states now. Let me see who. Oh, Asher had brought up the state suspended. Okay, there is, that, and there could be others that we have there, but these are the main ones. Suspended, I think, might be maybe the only other one that you would have, and it deals with, okay, another task that an operating system might have, um, and and I think if I recall, um, uh, and maybe the way that they, okay, drew the sort of diagram, um, a process definitely in the running state or blocked state can go to the suspended state. Okay, and then whatever state it came from. So you have the diagram in the it would be week 4. Okay, and I think they might have labeled, okay, the diagram 4.1.7. I don't know if that's the section, label, or sort of the diagram or figure. Okay, but in there they show, it was the, okay, or no, it might have been maybe not the running state. I forgot. I'd have to take a look. And I thought it showed two states. Okay, it might be the ready and block, or and blocked. Okay, that a process that is in the ready state can go in the suspended state. Okay, but if it's, okay, if uh, if we if the system removes, okay, or moves it out of the suspended state, okay, it would go back to the ready state if that's what it was in when when it was suspended. If it was in the blocked or waiting state, okay, then um, I'm gonna have to. I just have to sort of. I should double check it, but look at that figure or section in the week 4 reading in the textbook, and it was definitely 4.1.7. There was the other statement. I think I saw that it was blocked, not running. Okay, but if it was suspended and it had been in the block or what we call waiting state, then when it resumes, okay, it will go back into that state. So whatever state it was suspended, and there were two, it goes back to that state once it resumes. And there's sort of different, well, I use the term pause. Okay, but these are the main, okay, the states that we have. Like I said, your reading material included that additional one. Okay, oh, with ready and block. Yeah. Okay, so I was right. I mean, I don't necessarily have a photographic memory, but sometimes I can, something stands out and it's almost like in my head, or, it's like I can see that figure. I know it was in between, there were three, and there were, definitely, triangle, I think ready, running, and block, and I think ready was on the left and block was on the right, and suspended was in the middle. And I was pretty sure it was those two. It would sort of make sense. Okay, they're not in the middle of executing stuff. Okay, but we're in it, really, not really in it. Really won't be much to mention. When that state would be a state if the operating system incorporates that. Okay, so okay, now for the scheduler to do its thing, um, okay, maybe one additional question, okay, to to ask, okay, having to do with if an IO operation completes, or that would be sort of the the most common, okay, reason a process would be in the block state. What would, in a way, let the system know what would happen in the computer system that would let the operating system know that that IO operation completed? Okay, it deals with an IO device, like David had said. Okay, how would the system, the computer system, and of course the operating system be alerted, okay, to the fact that, okay, no, that's the process requesting an IO operation. Okay, I'm talking about when the IO operation completes. The process is in the block or waiting state, definitely not having instructions executed. Okay, but when an IO operation completes, okay, what would, okay, in a way alert the system, and in a way the operating system, that that operation completed? Okay, obviously an IO operation deals with an IO device. Okay, yeah, the device controller, and what does it do? Okay, the notification is done via, the device controller is it's hardware. So how would it notify the system? Nope, not a flag. Oh, and okay, okay. What about the bus? What happens? Okay, or what goes on? Okay, okay, okay. Signal, but what is that signal? So what would we call that kind of signal to the CPU? Swarna has mentioned. Okay, that goes over the bus. Okay, and not being a flag. Oh, yeah, okay. Well, it's the device controller that does, but what does the device controller do to let the system? What do we call that? What do we call that signal? I know it's sent over, okay, the bus, but okay, the device controller, the signal, okay, that it makes is called a interrupt signal. Yeah, a hardware interrupt. Okay, so the process, okay, uh, dealing with that I/O operation is in the block state, uh, and so at some point, okay, when the operation completes, the device controller generates a hardware interrupt. Okay, some other process will be in the running state, and executing on the CPU. Well, we're assuming that, but if the kernel, when the operating system was running on the CPU doing something, the hardware interrupt would get okay. Interrupts would in a way disable, but not okay removed. Okay, once they're re-enabled, then the interrupts are would make their way and interrupt the CPU. But assuming that we have a user process running on the CPU, okay, that device controller, okay, executes a hardware interrupt, okay, uh, and then the current running process, okay, is paused, okay, ends up in the ready state, okay, and the hardware interrupt is handled by the kernel, and the interrupt service routine, okay, deals with it, sees that, and it's, the device driver, it sees, oh, this I/O operation completed, okay, and that operation dealt with, was okay requested by a particular process, so the operating system will go to okay that process, okay, and change its state from block or waiting, whatever we want to call it, and set it to the ready state, so that then eventually, okay, it will okay be dispatched to the CPU. Not necessarily right away. Whatever process that was in the running state, if there was one, um, will resume. Okay, but now that process, okay, is in the ready state. So in a way, that's how a process that's in the block state ends up getting in the ready state. If the resource was an event or some other kind of resource other than like an I/O device, then when that event or happens or resource becomes available, okay, the um, uh, basically that has completed, and then what it would mean is that resource would be destined to that process, that event when it occurred. It's that process that was waiting for that event to happen. Again, the operating system, okay, goes to that process and changes its state to the ready state, so that then, okay, it ends up in the pool of, okay, processes that are in the ready state. Okay, now, well, in order for the operating system to know or have at its disposal, and it, and and a quick and easy, okay, to get at all the processes that are in the ready state. Okay, you need to implement, okay, within your system in some way a data structure, okay, to provide that list or group of processes in the ready state. And the same thing for all the processes that are in the blocked or what we call waiting state. Okay, so I don't know if they do kind of consider these in a way data structures. The and okay, okay, um, um, uh, data structures utilized by the scheduling algorithms or routines or routine. Definitely, okay. The For the CPU scheduler. Okay, and really, number one, I should really kind of maybe leave that off. I mean, I include it in here. I mean, here they use the term job. Okay. Now, okay, the data structure that they use doesn't necessarily have to be okay what we normally think of for a queue. Okay, normally we think of first in, first out. Okay, where the operators are NQ, add on the back, okay, and remove from the front. Okay, normally, like, I know when I taught data structures, that, discussing implementing, okay, well, there were a number of linear, okay, data structures. You can either implement what we call FIFO, okay, just write that, you know, Okay, these cues that the scheduling cues we have could be a FIFO, first in, first out. That's what FIFO means. Um, uh, if you hadn't known it already, um, they could be okay. The data structure for that particular scheduling queue. Okay, originally when you had CPU scheduling and other scheduling algorithms, or routines in an operating system, probably the data structure used um, was a queue, first in, first out. So the name queue, okay, is just sort of standard name that they give it, but it doesn't necessarily have to be that type of data structure. Okay, and we can actually implement like a first in, first out queue using a linked list or an array and so forth. So we had the two operations, the major ones, okay, were NQ adding, and you added it to the back, okay, it's a list, and DQ, remove, one from the front, okay, and so, okay, the, okay, definitely the CPU scheduler. Okay, definitely, is involved, okay, or and utilizes the ready queue. When the CPU becomes free, that's where it goes to. However, it might be implemented. Okay, and typically that data structure, whatever might be used, whether it's a FIFO queue or not, Linux, they are the ready queue, but it's really a binary search tree because of the type of scheduling algorithm. So it's really a tree, not, and they don't use the name ready tree. They call it the ready queue, but it's organized, okay, in a tree-like structure because of the algorithm. Okay, but what's in the ready queue are actually all the processes, okay, that are in the ready state. Okay, now, okay, the device queues, okay, have to do with the block uh, or waiting state. Okay, every process that is in the block, or we call it waiting state. Okay, I'll use block since that's what they use in the textbook. Is going to be okay. It won't be in the ready queue because if it's not in that state, it's not going to be within that queue. Okay, it will be in a device queue. Okay, remember we have okay. Remember the typical operation that a process okay makes a system call for is an I/O operation. I mean there are others. Okay, that and that definitely puts it in the block state. Okay, and you know that you have a number of device controllers in your system. So for each one, okay, there'll be a separate device queue. Okay, and that device queues might be basically, you know, well, they don't necessarily have to be a FIFO queue, okay? Because when an I/O operation completes, okay, a process being in that queue could be at any place, probably a linear list. So if the process is in the middle of the list and the I/O operation completes, okay, then the device controller issues that hardware interrupt, so the operating system would know, oh, I that the device controller definitely the information. Okay, it lets the operating system know and the device driver know that which process the I/O operation belongs to. Okay, and so the operating and the device controller or the device driver, I should say, um, okay, would then know, oh, that process is in the block state. It would be in, like if we want to imbue the device driver with human, okay, attributes, it would say, oh, it's in my device queue. Okay, it would not need to go, so each device, for each device controller, you have a device queue, and a process would be in that queue, okay, for that device controller if the operation dealt with an I/O device connected to that device controller, and it would be in the block state. Okay, it would definitely be there. Now, okay, they don't use a different name. What about other operations that don't deal with an I/O device? okay, there might be additional, cues. They still call them a device cue, even though it doesn't deal with, okay, but they might think of a resource or events as, okay, in a way, a kind of device. So they might have additional device cues, not, dealing with any device controller, but to, place a process in that, queue, okay, while it's blocked, waiting for, okay, an event or a resource. So there's more than one. Okay, and so those are the two main ones. Okay, how are they implemented? Okay, we still have. Okay, fortunately, in this class, I've you guys are gonna get a little bit ahead. Okay, so how are, okay, these cues, okay, actually implemented? Um, okay, and what does it mean that a process is in that queue? Okay, um, okay, what it, okay, um, you, okay, well, and it might depend on how it's implemented. I drew that line sort of wrong, or sort of there. What it is, okay, is you, well, you might set up certain things. You might not create a data structure, or it's not you, the programmer, but the operating system coder. You don't create a data structure like you would do in, an application. I haven't talked about the job queue. Okay, I'll get to that. But you don't actually like create a data structure like you do in an application program. It all is, okay, having to do with the, okay, process control blocks. Okay, if a process is in the ready queue, okay, okay, there'll be a ready queue, pointer. Okay. In, okay, every process control block. Remember, there was, okay, the CPU scheduling section. Okay, what, and they'll place what pointer or pointers. It depends on, okay, the way, what kind of, in effect, data structure that the process control blocks of processes in the ready state, okay, how it will be organized. I mean, the binary search tree, you might have like maybe 3 ready queue pointers, one for the parent, one for the, okay, left child, right child, and so forth. So it depends on, okay, the data structure, the structure of the kind of data structure you would use. Basically, you're placing the, you're not actually moving the process control block. You're mainly just manipulating pointers, okay? But you're, basically putting that process control block in the ready queue if it's in the ready state, okay? And the same thing you would have, okay, 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 definitely. Okay, for each device queue that you would have one or more pointers. Probably there, maybe just one pointer. Okay, and then the operating system would definitely have, okay, a pointer pointing to the first, process in, okay, the ready queue, the first process in each device queue. So, basically utilizing pointers. Okay, if the process is in the block or waiting state, okay, then the operating system goes to its process control block and manipulates the pointers for that device queue to put it in that hue. So that's the basic way, okay, that we implement those particular scheduling hues. Now, I don't know if in the material they talk about other scheduling hues. Definitely, okay, there is a Reddit hue, and there's definitely going to be a device hues. Implementing that. Probably when you add a new, hardware to your thing, you add a hard, there's a device controller, and you have to install a device driver, okay, then there would typically probably in the operating system, set up a device hue. Okay, definitely, I think you have to reboot the system. So, okay, then process control blocks would definitely then have, okay, pointers for sort of the new device controller and whatnot. Okay, now, okay, so Chris was, asked about the job queue. Not necessarily every operating system might not necessarily have a job queue. That term job, okay, hasn't been used, okay, we use process instead of job. Um, if an operating system does, okay, have a job queue, okay, every process in the system, okay, would be in the job queue. Though, I mean, from my understanding, though, I might not necessarily have been remember it correctly, and really the job queue, okay, for this course is not necessary to, okay, necessarily remember it. But it was from my understanding, because back when I took operating systems, a batch, you know, uh, you know, uh, a batch, you know, uh, processing or an operating system that really only did batch processing, jobs. Still, whether it was uni programming or multi programming, okay, the job queue might not necessarily have been all processes in the system. Though I might be thinking of a different term. There was a word called job pool. Job pool, I think, were jobs that are not in memory but waiting to be loaded in memory so that they can be in executing. I don't know if I'm mixing up job pool with job queue. Okay, you might need to keep track of all the jobs or processes in the system, but what the job queue might be is the table of processes, like in your project, that array, okay, table array, the when I say table, really it's an array. So the job queue might be okay what the job queue is. What it might be is I might have done some research and I read my textbook again, the other one I used. I don't know if they talk about that in your textbook or the one I'm using now. And of course I might go elsewhere, other books and resources. But it might be that there's no definitive answer. So number one, okay, I just bring it in because okay, at one time and maybe some operating systems might still have okay a job queue. But the main ones are the Reddit queue and the device queues. Okay, definitely those are in all operating systems. Definitely ones that we know. Okay, iOS, iPad OS, and whatever they're calling it, Android, Mac OS, Linux, Unix, and Windows. They definitely have a ready queue. They might have ready. I think they usually only call it. They only really call it a ready queue. There's really only one, though. Okay, depending on the algorithm. Okay, I don't know if they consider it queues or a queue. Okay, but at least for most of the algorithms that we're gonna scheduling algorithms, it's sort of just the ready queue is really only one. Okay, so so that's needed in order to schedule processes, meaning that a process will get the CPU, execute there, but then end up blocked, or possibly if there's a suspended state, go into there, and you probably would need another queue to for processes that would be in the suspended state. So needed by the various okay scheduling algorithms. We definitely, of course, every operating system has a CPU scheduler. So in the few minutes that we have remaining, any other like questions, that you have? Let me just, I want to see, because I kind of forget. Okay, um, will, okay, uh, um, definitely talk, about and kind of get started on a scheduler that an operating system might have, but an example of schedulers that operating systems that do not have, this one, are Linux, Windows, Mac OS. Those are Unix, Linux, Mac OS. Well, they're all of that type, and Windows. And that is the long-term scheduler. Okay, okay, they it's also called the job scheduler. Okay, um, okay, it controls the degree, and that word also number, or the amount of multi-programming. What that would mean, degree would mean how many processes are in main memory. Okay, um, okay, and like Windows, Unix, Linux, Mac OS, if a process wants to create another process, it gets created. Okay, there's nothing to stop it from saying, or the operating system from saying, nope, you can't create another process. Okay, this a long-term or job scheduler. Long term because it executes infrequently. There's a long stretch of time from from the one time it executes to the next time it executes. It harks back to the day of when you basically had a batch processing system, and there was only a certain number of programs that can be loaded into memory. You had multi-programming, but you couldn't just like create another process and have as many processes in main in main memory as that you want. Okay, basically what would happen with, and the reason that long-term scheduler would execute is if a process, okay, terminated, completed its execution, definitely its memory, okay, space is freed up, and that would mean that the long-term scheduler would then be invoked in the operating system to go to the job pool, okay, okay, and choose, okay, a job to, okay, load into memory, and then it can begin executing, okay, begin its execution. Okay, now which, job would be brought in? That's where, and we'll stop right here. I know our class has ended. The right, the best one brought in, okay, the what you would use to decide that would be based on, okay, those two terms, CPU bound and IO bound. Okay, programs that are that. So that we've uh, okay finished. We've reached the end of our lecture today, so I'll stop the